Hello everyone. Good morning. In the past session on work energy power, I have explained the theory you need to study. You need to know before you start solving problems. Today's session, I will be showing you the applications of the concept you already got. I will be revising that also, and then some numerical problems based on it. Work energy power is a very important chapter in your class 11 coursework. Understanding work energy power will help you to understand the nature of gravitational force, electric force, electromagnetic force, and not only that, for your every competitive exam, concept of work energy power you need to apply, because some questions are always asked from work energy power chapter. That may be work done to compress a spring, maybe just work done by the strings of pulley, maybe work done to bring a chain at the top of the table where a part of it is hanging. This session I will be discussing one by one all those important concepts you need to know, need to remember, and simple application in solving problems. So let us start. Work, energy and power. We'll be discussing essential concepts and concept application. At first, let us know nature of work in different situations. Nature of work in different situations. Why? Because work done, you know, is dot product between force and displacement. So on an object, if a force acting at an angle theta, then to displace this object by distance s, say from the point A to the point B, A and B, this angle with theta, you have seen that W equal to the magnitude of force be F cos theta into S, that is F dot S. Dot product between force and displacement vector is the work done. And this theta may be equal to 0. For theta equal to 0, W is Fs acting in the same direction. You know, for theta equal to 90 degree, work done will be 0. And for theta equal to 180 degree, W will be Fs cos 180, that is minus Fs. So under these different situations, different cases, we will be calculating work done. That is, work done may be positive, work done may be negative. For positive work, then theta will be greater than 0 degree and less than 90 degree, greater than equal to, for positive work. And for negative work, theta will be greater than 90 degree, less than or equal to 180 degree. Then W becomes negative. If an object is pulled against gravity, I mean lifted up against gravity, in theory class I have explained, in this case work done by external agent will be positive. work done by external agent will be positive to lift it upward, but work done by gravity will be negative. Let us work on it first. Block of mass 5 kg is pulled by a force upward through a height 2 meter. Find the work done on the block by the applied force and the weight. Weight means that is gravity. So to solve this problem, we will apply the concept. Already I told you that work done by external agent, it will be positive work. 60 multiplied by 2. This is 120 joule. And work done by gravity, this will be negative because gravity acting downward, mg force. Displacement upward. So mgh cos 180 degree. What is m over there? 5. 5 you take 10 and h is 2. So this will be minus 100 joule. In the first case, the work done by external agent is positive, that we have seen, and in the second case, work done by gravity is negative work. Okay, let us think about next problem. 20 kg block is being pulled by a constant force 80 Newton. Coefficient of friction between the block and the floor is the block and the floor. Body is taken from the point A to the point B. Find the work done by each individual force. What are the individual forces here? This constant force is 1. This is not gravitational force. This is actually external force. So F external is 80 Newton. And what is the frictional force? FR is mu into m into g. That coefficient of friction given, it will be 0.3 into 20 into 10. So this is going to be 60 Newton. So external force 80 Newton and frictional force 60 Newton. You have to find work done by this external force and then work done by the force of friction. What is that? The displacement is 10 meter. So work done by external agent will be 80 multiplied by 10. This is positive because displacement is along the direction of force applied. So this much joules, that is 800 joules is the external work done. Clear? Now, what is the work done by force of friction? Force of friction, if we are moving the body, the object towards right, then frictional force comes into effect, it acts opposite sense. So displacement is being done in a direction opposite to the force of friction. So work done by force of friction will be 60 into 10 cos 180 degree. So this will be minus 600 joule. Clear? Very simple application is there. Just work done by the force, work done against the force. Next one, you see, block of mass 3 kg is being brought down by a string. Pulley must be there. Without pulley it is not possible. You can hold it also. Let us assume that with the help of this pulley you are taking it down. Okay. This force is 3G. Tension is there, which is acting upward. Block acquires a speed here, which is given by 2 meter per second when it goes down by distance 30 centimeter. Okay? Then question is, find the work done by the string in the process. Understand what I say? In this case, you need to find tension of the cord, and for that there is an acceleration. The acceleration it acquires 2 meter per second. What are the forces acting on it to get that acceleration? There is acceleration created here. No, this you must agree with me. Acceleration is created over there. What acceleration? It is because this tension and weight, that acceleration downward be A. So if you go by equation of motion, that mg minus t is going to be ma. So t is equal to what? M into g minus a. How to get the value of a? Because v equal to, this body has got velocity 2 meter per second when it travels 30 centimeter. So v square equal to 0 square plus 2a into s, that is 30. V is what? 2. 2 square equal to 60a. This implies a equal to 4 by 60, that is 1 by 15 meter per second square. Okay. So from there t you can find, t is equal to mg minus ma. Just put it there. Therefore, from this equation, t is going to be equal to m. M is 3, g is 10, and a is 1 by 15. Okay. But tension is acting upward, object is going downward. So work done will be what? Dot product t into force into distance, that is 30 cos 180 degree, as they are acting in opposite sense. So t you got, this is 3 into 30, 1 by 15 and minus 1. So 900 minus 6 into minus 1 joules. So this is nothing but 894 minus 894 joules. Am I clear? This work done has to be negative. Now consider the case of this etude machine. Two unequal masses, 3 kg and 4 kg, attached at the ends of light inextensible string passing over a pulley as shown in diagram. This is the diagram. Okay. Say this one is 3 kg and this one is 4 kg. 3 and this is 4. Now see the question. System is released from rest. Find the work done by string on both the blocks in 2 seconds. So this problem when you are going to solve, there is application of the concept you already got there. Work done by the tension, work done by gravity we have studied earlier. If the mass is moving against the tension, that work done will be negative. If it goes due to the application of tension, that work done going to be positive. Now see the question again. If the system released from rest, find the work done by the string on both the blocks in 2 seconds. There is a tension on right side. there is tension on left side also, isn't it? Are they same? Answer is yes. Tension will have the same value, that is equal to T. Okay? This concept already explained in Newtonian mechanics. This is 4 kg and this one 3 kg. So tension will help 3 kg to move up because its weight is less, and tension will oppose to move this 4 kg downward. Whatever acceleration there here upward, the same acceleration will be there in downward. So write the equations of motion. What are those? That 4g minus t equal to 4a and t minus 3g equal to 3a. Okay? 4g minus t equal to 4a and t minus 3g equal to 3a. So let us find acceleration from here. You take g equal to 9.8 meter per second square. If it is given, you have to take. If it is not given, then also you prefer to take 9.8. Because just by adding here, what do you get? This is becoming g equal to 7a. So a will be g by 7. G is 9.8 by 7, 1.4 meter per second square. Acceleration is this. If you get the acceleration, then tension can be found out. This value of t going to be from 2. T is equal to 3 into a plus g, 1.4, 9.8. So this will be 11.2 Newton. This is nothing but 33.6 Newton. Clear? Tension is this. Now, in the first case, tension is pulling 3 kg upward, and this work done is positive. This I told you. So, what is the work done by the tension in this case? So, work done to left, work done by tension. This we are only going to do. By tension, work done to left 3 kg mass will be what? Work done by the tension to move 3 kg upward will be this t into displacement. Isn't it? Displacement what? That we don't know. But time we know, through which it is in motion. So displacement you find by using the relation that A is equal to half a t square. Half into a, what have you got? 1.4. T square is 2 square, that is 2.8 meter. This is for S. S means S1, S2, whatever you say. T into S1 is T. The tension you got 33.6 into 2.8 joules. Okay. So right now I can use the calculator to show you. It is just a minute. Let me find the calculator. (33.6 into 2.8). So it is 94.08 joules. And this is positive because the angle between them is 0 degree. S1 displacement is along the string only, so it is positive work. What about the second case? I mean, what is the work done by tension in this case? Tension here did positive work, but here displacement, whatever displacement was there, that is 2.8 we found, no? The displacement you got 2.8, but that work done will be negative. I am writing it here. This work done going to be negative. In this case, work done by tension will be Ts cos 180 degree. Clear? That is tension you got here. So just multiply and this work done is going to be negative. Is that clear? Understood? So in the first case, work done positive, that T into displacement. In the second case, work done is negative, that is minus T into S. And value will be the same, obviously, because T and S remains the same. So here the answer going to be minus 94.08 joules. Concept is clear. Work done by force, work done against force, work done by tension force. Now let us go these kind of things. Application of vector in cases of displacement in 2D and 3D. But remember, we are going to apply it in vectors, vector. With the help of vector you can do it. So it will be better to apply the concept of vector here. I will be discussing the concept first and then we will calculate work done. Suppose the force vector F is equal to Fxi, Fyj, Fzk. And displacement vector ds is dxi, dyj, dzk. Okay. So w equal to f dot dx. This work done how to find? Two vectors r1 and r2 are there. Say R1 is A1i, B1j, C1k, A2i, B2j plus C2k. Then R1 dot R2, you have seen this before. I am just writing the result. A1, A2, B1, B2, C1, C2. Very useful formula to get work done very first. So this time work done going to be what? Fx into dx, Fy into dy, Fz into dz. Am I correct? Just consider one 3-dimensional case. 2-dimensional will be the same thing. Let us find in case of 3D. Question arises this manner. Problem on this: find the work done by the force F is equal to 3i minus j plus k to move. Find work done by this force F to move an object to 1, 3 to 5, 3, 6. Okay, this force is given here. A is the initial position, B is the final position. So how do you account for the work done? That work done going to be W equal to F dot S. F dot AB. This is equal to 3I dot, let us find AB vector. I know you have done concept of position vector and the displacement vector. So AB is what? It is position vector of B minus, but position vector of A. Okay. What is position vector here? Position vector B here, 5 by 3j, this minus, okay, so this will be 3I plus 2j plus 3k. This is AB vector. So you just find the dot product of this F with AB. 3I. So this is going to be, I have explained you that force into displacement, this. So there will be 3 into 3, 9 minus 2 plus 3. That is 10 joules. Or you write 10 units. Clear? Now another kind of problem may arise here. Find the work done by the forces F1 I minus j plus 2k, I plus 2j minus k, F3 equal to 2I plus j minus 3k. To move, work done by these forces, to move an object from A 312 to B 2 minus 1 4. How to solve this problem? Force is given this manner to move an object from this point to this point. Remember, the concept is the resultant force. When you calculate work done by an external force, this external force equal to sum of the forces. Those forces we have taken F1, F2 and F3. So you need to find the resultant force and then use dot product. The resultant force F, F1, F2, F3. Isn't it? You find the resultant force, then use the previous formula. The resultant force in this case, if you add 6I, j, 2j and here minus 2k and write the displacement vector. This minus this, that is minus I, this minus 2j and this thing minus this thing plus 2k. So you got displacement vector, you know force vector, you just use dot product. So required work is going to be F dot AB. Again the same manner, 6I plus 2j minus k dot minus I minus 2j plus 2k. Okay. So take the dot product here. I hope you are understanding. So it is minus 6, minus 4, minus 4, minus 14 joules. Minus sign may be there. Concept of negative work we have seen before. So by actual calculation it may be there. Here now let us solve this kind of things. Work done by variable force. How do I account for this? By variable force. The concept I have explained theory class, will be revising it today again. That is variable force. Work done by variable force. How to find work done by a variable force? This I told you there are two ways to get work done by variable force. You can get it by integration or by calculating area. Suppose a variable force take the object from here to here. This we have seen in the last class. This is F. This is displacement x. Work done to take the particle from the point A to the point B will be what? This is area. This area will give you the work done. So basically you remember this formula, W equal to integration F dot dx. Both are treated as vector quantity over the whole path. Okay. So let us take an example. Example 1. Calculate the work done. Find work done by F equal to 3x square. Okay, let us take 3x square I plus y cube j to take an object from 2, 4 to 6, 7. We have to find work done by this variable force to take the object in 2D from A to the point B. How do I account for this? Formula already have told you that fx dx, fy dy, fz dz, isn't it? Or go by dot product concept. So AB vector you find. AB vector is what? This is 4i plus 3j. What problem? We cannot find it by using the dot product between F and AB, which force is changing along x-axis, along y-axis, both the cases. So we go by that concept where ds vector we take as dxi, little displacement along x-axis, along y-axis, and then calculate the network. This is the concept here. Network is always area under the curve, but you first calculate one part. So this dxi plus dyj is there. Therefore dw will be what? F dot ds. Now it is 3x square dx plus, you all understand, because function of x will go with dx, function of y with dy. Now work done by external agent will be integration of dw, integration of 3x square dx, y cube dy. This is from what to where? 2, 4 to 6, 7. You can write this way. 2, 4 to 6, 7. 2 to 6, x coordinate change. 4 to 7, y coordinate change. Clear? So what you have to do there, you have to split. First integrand is on x, 226 3x square dx plus 427 y cube dy. Am I correct? Done. Now you integrate and put upper limit minus lower limit. The same concept here. Just a minute. So this, when you integrate, it will be 3 x cube by 3 226 plus y4 by 4 427. So this will be 6 cube minus 2 cube. This is 7 to the power 4, 4 to the power 4 by 4. 216 minus 8, 208. For this part, let me use calculator. That is just a minute. This is 2401. That 2401 minus 256. So this is coming 208 plus 536.25 joules. So this is going to be 744.25 joules. Clear? Understood? Now we are going to discuss this kind of problem, work done by using force displacement graph. Just to have seen that, just have explained that work done equal to area, isn't it? Work done is equal to area. This area given in a simplified form, or work done is a simplified form means rectangular shape, maybe trapezium shape, whatever. That area of trapezium you can find, area of rectangle you can find. But in this case, when the force is variable like this, then the work done we got here should remember that this work done is actually this area. Okay, this is the concept here. So from the graph, I am categorically, if I mention, then that work done will be not this way. This way it is possible. Then equation of curve I have to tell you. Shape will be given this manner. Just I am writing this way. Find work done. Just this way. A force F acting on a particle moving in a straight line varies with distance as given. That is x, y. What is it? And this force they have given 10 Newton, this is 12 Newton, and the force at this point given, this is not Newton, sorry, this is 10 meter, 12 meter, and this one 20 Newton. You have to find the work done to take it finally at this point, say 30 meter. Okay? How to find the work done? The concept just I told you can be used, that is area under this curve. Okay? Since the force at this point is 20 Newton, no integration is required. It will be just work done. Because force versus displacement graph only given. Here it is in meter, means that is displacement we have taken here. And this is the direction of force. 20 Newton acting to move it from 10 to 12, then force magnitude gradually reducing to take it from 12 meter to 30 meter. So work done will be the area. This area will be what? You can easily find. Required work done. I did not write the sum because it is quite obvious. Force acting on a particle is as shown in figure. Find work done. So required work will be this area. Area of this diagram A, B, C, D. Trapezium, no? It's trapezium. Area of the trapezium. This is nothing but trapezium area half base into altitude. 20 into 20. Base is 10 meter to 30 meter, 20 meter, and this one 20 Newton. So get cancelled, it will be 200 joules. Okay? For a curve, equation of curve will be given. Okay? Just let me show you another example based on this concept where it is not given in this form. Say the problem is like this. Force acting on a particle changes according to this graph. F versus X. Okay? Force changes with displacement according to this curve. That is, say I am writing x square equal to y by 4. Changing according to this relation. Okay? Your problem is to find the work done for the displacement. Work done for the displacement from x equal to 1 to x equal to 5 meter. Okay? Force changing according to this relation, you have to find the work done. You can write that this is instead of y is along force, no? You can write x square equal to that F by 4. Okay? But here we know the concept that it is the work done which is equal to the area bounded by the graph. So this is your x equal to 1, 1, 0. This one is 5, 0, and this is the case of work done. So how do I account for this? Work done will be W equal to F into dx. Here y plays the role of F. So F is what? 4x squared. They have given this equation and you should integrate from 1 to 5. So this is coming to be what? 1 to 5, f is y, y is 4x square, so f is also 4x square dx. Understood? This will be 4x cubed by 3, 1 to 5. So this is nothing but 4 by 3, 5 cube minus 1 cube, 124 joules. Okay, you just multiply and find 4 into approximately this thing, so it is 164 joules. Clear? Hope you have understood how to find work done by variable force. Now let us solve some problems from spring block system. Okay, how work done we have to calculate in this case for spring block system. I just explained the concept here. There is a spring and this has spring constant K. This spring is being pulled by external force F external, then spring constant is K only. Spring constant is K only. So W equal to W you have to find for spring block system. First let us know work done positive, work done negative. Suppose the spring elongates by elongation be x by external agent. So work done by external agent will be what? Half k x square. Force is what? Force is kx developed by the spring. So kx acting this way, and this external force is applied, same force in forward direction. So if you find W by using this formula, it will be by external agent fx cos 0, so 0 to x, and f is kx. This derivation you know, half k x square. This is work done by external agent. Work done by spring force is what? Work done by spring force will be minus half k x square, because this force is negative, or object is displaced towards right, force is acting towards left. Let us work on it. So let us do one simple problem here, that is work done in extending a spring by L0 be W0. Find the work done for further extension. Find the work done for further extension to N0. To L0. How do you account for this? How do you account for this? You know, just work done W0 when you have extended by L0. For this one, you have to go for second case, L0 already there, 2 L0 more. So extension L0 to 3 L0, not L0 to 2 L0. Let me show you. So when you are answering, this W0 will be what? Half K L0 square. Direct by external agent is doing. This is number 1, not by the spring. Spring negative. In the second case, when it is extended up to L0, this initial extension L0, final extension to L0 plus L0. This is 3L0. You have to find the work done in this case. Okay? How to find work done in this case? We go by the formula. W equal to integration kx dx. L0 is the initial extension. 3L0 is the final extension. So lower limit, upper limit will be according to this consideration. Lower limit is some initial moment, final is the final moment. Initial extension L0, final extension 3L0. So it will be L0 to 3L0. K will be outside, integration x square by 2. Okay, so it will be K by 2 into, put 3L0, 9L0 square minus L0 square. So W will be what? K by 2, 8L0 square. So 4KL0 square. What is KL0 square from here? With W0 is known, it is 2W0. You substitute 4 into 2W0, that is 8W0. Okay? This is the power of mathematical technique applied to physics when you are calculating work done in such a situation. Okay? Writing another sum for you which will help you to understand better. Just I am drawing a diagram, then I will tell you the sum. This spring has some spring constant given. Wait a minute, sorry. This spring constant, say K equal to 200 Newton per meter. There is a block attached at the end. Okay, this is the ground. This is ground. On ground it is lying. Horizontal surface. Okay, the surface. You have applied a force on it. Some external force is applied, okay, which gives stretching of the spring by 10 centimeter. Okay, you have to find the net work done. So let me write the question here. In this diagram, a spring of force constant 200 Newton per meter is shown. Okay, attached to a block. It is displaced by 20 centimeter. Okay, question is what then? Find the work done by the force, work done by the spring force WSP when the block is in equilibrium, and the second part, net work done the block net work done when it attains maximum velocity. Okay, this is the question. Question is a bit difficult here, isn't it? Why difficult? Because this is not a straightforward calculation. You have applied a force displaced by 10 centimeter and then released from there. Okay, now when it attains equilibrium, comes back to this point, it acquires the maximum velocity, isn't it? So your problem is to calculate the net work done on the block. How to account for this? When the block is in equilibrium, it will attain the maximum speed. Okay, so first you calculate here that work done equal to minus half kx square. Why? Because this is work done by spring. They said W spring will be minus half kx square. K is given 200 and x is how much? 20. Account for this. So minus 100.04. It is minus 40 joules by the spring, and this is negative work. Negative work indicates what? The work is done by the spring. And next part, in equilibrium, the speed is maximum. That you know. Okay, so work done will be what? Force into displacement. Force is how much here? Force is how much here? Tell. That is k into x. How much is k into x? 100 into 0.2, 0, and that x is what? That is also 0.20. So this is going to be 4 joules. Clear? So net work done on the block going to be equal to minus 40 plus 4. This is equal to minus 36. Clear? This is just W and this is W spring. So sum of these two will tell you the net work done. W is minus 36 joules. Clear? Net work done on the block. It's okay, because spring will bring back to original state. Maximum velocity it acquires when it is at original state, isn't it? It is displaced from here to here, now released. Then spring works. First time you have worked against the work is done by the spring against the displacement. Displacement this way, spring is working leftward. Force applied by the spring leftward. Next time spring brings it back. Okay. So work done is simply force into displacement, that is becoming that is 4 joules. That's why it is positive work. Clear? Next, work done in frames of reference. Suppose you have displaced an object, you are situated on a car or a train, whatever. You have displaced an object. You are standing here. Displacing an object to take it from the point A to the point B. This point A to the point B. This displacement you have given, say, x. Then how much work done by the force with respect to you? How much work is done by an observer standing outside? Observer now standing here. I mean another observer. This is not the same observer standing here. This car or train moving with some velocity, so that when you have displaced it by x with respect to this, with respect to this is observer 1, this is observer 2. Displacement with respect to the observer 2 will be not x. This object moves here, say. Object goes there. When that car, when this object is moved by distance x, say the car travels from here to here. So that x displacement is there. It is from here to here. No, AB it is there. A to B it is there. I mean this x is there. But this x is due to motion of the train. So in the frame of reference, in the frame of reference of the car, in the frame of reference of the car, work done of the car means by the observer O1, by observer O1, work done will be what? The force, external force have applied, F external into x. With respect to this observer, how much work done will be there? With respect to this observer here, how much work done will be there? That will be, this is WO1, this will be F external x plus x. So work done will be different for different frames of reference. I just give you one simple example based on this. Suppose the car in the diagram, the car is not very prominent here, okay. Imagine this is a car. The car in this diagram moving with a speed of 60 km per hour. The passenger O1 displaces this mass is say 10 kg. Passenger displaces passenger O1 displaces the object by 2 meters in 10 seconds. Find the work done by the passenger as seen by O1, find work done as seen by 1, work done as seen by O2. How do I account for this? Just think, then I will solve. The formula I have already given. Formula already given. I forgot to give friction coefficient. Mu is equal to 0.2 here. To move, frictional force is there, that is 0.2. So work done by external agent against the friction, work done by observer 1 W01, O1, this observer who is situated in the car, and work done with respect to this observer, different frame, different work done. So just account for the work done by the against the force of friction by the external agent. Okay, displacement of the load is given 2 meter in 10 seconds. Why this information given 60 km/h? Because you want to find big X from there, isn't it? So here W01 will be mu mg into 2, isn't it? Mu mg into 2. Mu is what? 0.2, and weight of the block 10 kg block I stated, 0.2 into 10 into 10 into 2, that is 200 into 0.2, that is 40 joule. Wait, mu mg into 2. M is this, G is this, and displacement 2, so this is 40 joules. But the observer who is standing here, with respect to him, how many? How much work is done? So work done with respect to observer O2 will be that same mu mg against the friction, x, the displacement you have done 2 meter, plus displacement of the car. So car displacement you find x equal to displacement of the car, which is nothing but that velocity given over there, no acceleration, v into t. 60 into 5 by 18 into t. T is how much? They have given in 10 seconds. Am I correct? Hope you have understood. So 6, 10, 3. So this is 500 by 3. So this will be added over there. Mu put 0.2, 10, 10, 2 plus 500 by 3. Is that clear? Hope you have understood. Now work done in conservative forces. Work done in case of conservative forces. How do I account for this? Work done in case of conservative forces. What are the relations available there, and concept of conservative force? Concept of conservative force I have explained briefly in theory class. Work done in case of conservative force. It is path independent. Object is taken from A to B via this path. Path 1 via this path. 2 or via this path. 3. WAB will be the same. For a conservative force, you can say this is definition of conservative force only. WAB is W1 or W2 or W3. Whatever direction you take, this work done will depend on the initial and the final position. So for conservative force, work done will be the same as before. What is that? This I have explained in problem like W equal to, say we are taking an object from some point, say A 214 to B 3 minus 2 6 by the application of a force say I plus 2J minus 4K. How to find the work done? This is for conservative force. What path you have followed, it is not dependent on that. So W will be simply F dot AB. This calculation we have done, so I am not going to do. I have not mentioned along which path it is being taken. It can be taken in along the path 1, path 2 or path 3, path 4 also there. Any path you take, it depends on these two coordinates A and B. Clear? So F dot AB, I plus 2J minus 4K dot AB. AB vector is I, that is minus 3J plus 2K. I am just doing it to make you understand that path is not important here. Whatever the path is taken, it will be the same thing. Okay, example 1. Let us calculate another one. Object is displaced from, second problem I am discussing, an object is displaced from A 2, 4 to B 4, 7. Okay. Under the action of force F equal to 3xi plus 2y square j. Find the work done. This kind of problem also we have done. Why I am doing this? Just I am telling you that this actually happened in case of conservative force. So how to find the work done in this case? W will be F dot AB, isn't it? AB is what? AB you know dxi plus dyj, and F is given here. So just take dot product and from the point 24 to 47. So if you take dot product, it is going to be 3x dx plus 2y square dy. So how to do this? This will be 2 to 4 3x dx plus 4 to 7 2y square dy. Just integrate 3x square by 2 2 to 4, 2y cube by 3 4 to 7. Concept already explained. For x you take change of x coordinate, work done along y axis, take change in y coordinate 4 to 7. Clear? Understood? So in case of conservative force, it is path independent. Whatever path you are taking, it is not required. Work done will have the same value. Here force magnitude is changing, no? What path, that I haven't mentioned. 2 4 to 4 7, any path with this force you take, work done will be path independent. But how to calculate work done in case of non-conservative forces? Work done when, can you give example of non-conservative forces? When forces are non-conservative. How do I account for this? Non-conservative force, you think about example. Frictional force, you have already studied, non-conservative. It is non-conservative. Then viscous force, it is non-conservative. How to account for work done when forces are non-conservative? Okay? Here work done is not path independent. It depends on the path. Okay? If you are taking an object from A to B via this path, work done be W1, this work done be W2, if you take this manner work done W1, here it is W2, this way it is W3. This work done W1 must not be equal to W2, must not be equal to W3. Please keep this in your mind. For non-conservative force, work done is not the same. When force of friction is present, it happens. Let us see. Let us see how to account for non-conservative force. Here, I am just discussing with one example here. This is the inclined plane. Your problem is to find the work done to move an object up the inclined plane from bottom of the incline to the top. Here I am writing the question. Just explain the situation first. This height of the top of the incline is given 10 meter. Coefficient of friction is given to be 0.40. Angle of inclination given to be 60 degree. And length of incline, I mean here to here. Just a minute. This length of incline, we have taken this one as say 30 meter. Okay? L equal to 30 meter here. Question is, find the work done by applied force to take it from A to B bottom to top, an object of mass two kg is taken from A to B. Okay, up the inclined plane whose height is 10 and length of the incline is 30 meter, and coefficient of friction is given here, that is 0.40. Question is, find work done by external agent. Find, and then find work done by the force of gravity. Third one, work done by force of friction. Okay, let us account for this. And also you calculate work done in the round trip. Find the work done by gravity in a round trip. External force is not there, it automatically goes down. You leave it there, automatically goes down. Here work is done by or against the force of friction. Friction only will do work. Let us do step by step. Okay, W external, how do I account for this? This load at any arbitrary position has two components, you know. mg, this way mg sin theta, and this way mg cos theta. We have to find work done accordingly. Just a minute. বাকি এই বাল্বটা নিয়ে নিচে চলে যাও, খোলা আছে? না So work done by external agent will be equal to this mg sin theta. I mean force will be this mg sin theta only. Okay. So W external will be what? This displacement, you know, mg sin 60 degree into how much? Just a minute. Work done by just a minute. Wait. When external agent is moving it upward, this work done will be done against the force of friction, isn't it? But the displacement of the object is along the direction of force applied. How much force the man should apply to take it in upward direction? That force will be equal to frictional force. Frictional force you know, that is mu mg cos theta into S. Mu stands for what? 0.40. That m how much I have taken? 2 kg. 10 cos 60 half and displacement 30. Idea is clear? Just simplify it. This will be that is 4 into 30, 120 joule. Next one, work done by gravity will be how much? Work done by gravity, W G, gravity I am saying, this will be this mg sin theta into displacement, that is 30 only. Just account for this. And the third part, work done by friction. Work done by friction will be negative only. This number 3 and number 1 will be similar. Number 3, work done by friction will be minus 120 joule. Work done by gravity, minus mg sin theta into 30. Why? Because gravity acting downward and you are displacing upward. So you substitute the value here. That mass is known, 2 kg, 2 into 10 sin 60 root 3 by 2 into 30. Simplify it. Clear? Work done by gravity in a round trip will be how much? When it is being moved upward, then minus. But when it is going downward, then it will be plus. This calculation, that is 2 minus 300 root 3, here it will be plus 300 root 3. Okay? Work done by gravity in the round trip will be minus 300 root 3 plus 300 root 3, that is equal to 0. Hope you have understood. Okay? So practice similar types of sums from your textbooks, from H.C. Verma and from the worksheet I have given.